Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 13. In last lecture, we were discussing about the physical features and unresolved issues in the flow over compressor and turbine blades. And we have realized the flow over the suction surface of both the aerofoils, let it be compressor, let it be say for turbine, for both the cases, you will be having many difficulties and challenges. And these days people they are exploring the possibility to resolve those issues. Now in sense of understanding what we say lifting force, we have correlated our lifting force with the CP distribution for say particular compressor aerofoil. So we have discussed what will be the CP distribution for C4 aerofoil, for double circular arc aerofoil and NACA 65 aerofoil, and we have realized the shape of the leading edge, that's what is very important. Basically that's what is handling your flow acceleration initially happening near the leading edge. And on trailing edge we will be having the flow that's what is getting diffused both on my pressure surface as well as on my suction surface. Then we have introduced a new parameter, that's what is called diffusion factor. That diffusion factor, it was included by NACA or say NASA in say 50s and 60s based on say their experimental results on cascade. They have put with the number, that's what is called diffusion factor. So how my flow that will be behaving on my suction surface, that's what will be deciding the diffusion factor. And we have correlated this diffusion factor with flow angles, and one more parameter we have introduced, that's what is our solidity of the blade. And that solidity we have defined as a chord to pitch ratio, where pitch that's nothing but it is 2 pi r and to radial distance divided by number of blades. We have discussed about say high aspect ratio blade, we have discussed about the low aspect ratio blade, and we realize by changing the number of blades, basically we are changing the diffusing passage between two blades. This passage, that's what will be responsible for rising of our pressure. So many times in order to check with the design, people they are considering diffusion factor as one of the calculating parameters. Many times people they are using diffusion factor as a parameter, and based on that assumed number they are calculating the number of blades which are required for both stator as well as for rotor. We will be discussing on this aspect in detail when we will be discussing say how to decide the number of blades. So let's move ahead with the next. So Liebling, he has given equivalent design diffusion factor. So according to him, he has proposed the empirical correlation. This empirical correlation, that's what is showing, it is a function of beta 1 and beta 2, as well as it's a function of my S by C ratio. And according to him, if we consider we are having off design condition, that's what he said, like it's a local change of incidence angle. Still we have not introduced this parameter, but still let me know and let me tell you, say when we say off design condition, that means my compressor it is been designed for particular mass flow rate and for particular speed. The change of your speed, that means your peripheral speed for velocity triangle, that will be changing, and if that's what is your case, my flow will not incident at the angle for what it is been designed. That's what is called off design condition. In line to that, we will be having say our mass flow rate, that's what is changing from design condition towards the low mass flow rate side, even for the high mass flow rate side. Under that condition also, in my velocity triangle, the parameter called axial velocity, that's what is going to change, and that will be changing my blade angles or blade incident angles. So according to him, he says like we can calculate equivalent diffusion factor, that's what is nothing but my incidence angle at that particular incident minus design angle, and this is what is a formula for that. He has introduced a parameter called K parameter. According to him, this K will be 0.0117 for NACA 65 aerofoil and 0.007 for C4 circular arc blades. Okay, and blade loading limitation, that's what is we are calculating based on this Liblin's equivalent factor. He said that need to be less than 1.6. So many times during the design incidents, people they are taking this parameter also into the consideration, but most preferably people they are going with the diffusion factor what we have discussed in the last session. Now let me introduce a new parameter, that's what is called say degree of reaction. So fluid, that's what is flowing through the passage, it will experience the acceleration, and because of this acceleration it will be having say reaction force, that's what will be acting, that is based on our Newton's second law of motion. This logic of degree of reaction that was applicable for say turbines. So initially before gas turbines, people they have designed the steam turbines, and based on that concept people they have started designing the gas turbines. So now this diffusion, this degree of reaction parameter, that's what is equally applicable here even for say compressor. So it says for compressor, the measure of conversion of your kinetic energy into potential energy through the diffusion can also be measured by using the reaction parameter. That's what is called, we are getting what we say in sense of our pressure rise. Okay, so this is what will be giving you idea like what will be the contribution of your pressure rise both by rotor as well as by stator. Okay, so from our second law we can say TDS equal to DH minus say VdP, that's what is dP by rho. If we consider our compression process to be isentropic process, we can say my enthalpy and pressure, they both are in relation. So here if you recall, we have discussed our TS diagram. Okay, on that TS diagram, my station 1, that's what is representing my entry condition, my station 2, that's what is representing my exit condition of rotor, and station 3, that's what is my exit condition from the stator. So you can say for stage my entry condition is 1 and my exit condition, that's what is at station 3. Okay, so let me put this parameter, say degree of reaction. This degree of reaction we can write down in sense of say static enthalpy rise in the rotor divided by static enthalpy rise in stage. So if I am writing that, we can write down say my enthalpy rise in the rotor, that's what is H2 minus H1 divided by H3 minus H1. So that we can represent in sense of temperature, we can say T2 minus T1 divided by T3 minus T1. It is nothing but my delta T0 in rotor divided by my delta T0 in the stage. For axial flow compressor, we are assuming our axial velocity to be constant, and as I told this earlier, we are having our entry absolute velocity and exit absolute velocity, that's what is coming to be same. So for that purpose, we can say my delta T for stage, that's what is equal to delta T0 for the stage. Okay. Now what we learn from our basic fundamental equation for the specific work, we can write down our work, it is m dot Cp delta T that's what we can represent in sense of m dot into u Cw2 minus Cw1. So this Cw1 minus Cw2, that's what we can represent in sense of our flow angles, that is alpha 1 as well as in sense of alpha 2 and beta 1 and beta 2. Now if I consider this as a control volume, and if I will be applying say my steady flow energy equation for this particular stage, we can write down for work done it is Cp delta Tr plus 1/2 C2 square minus C1 square. And this work done for my rotor I can write down it is Cp delta Tr, that's what is we are writing in terms of my aerodynamic work and thermodynamic work to be same. And this is what is representing my velocity component. If that's what is your case, and if we are using our velocity triangle, we can write down my Cp delta Tr in sense of angle tan angle. So this is what is representing my tan theta. Okay. Now if I will be putting that together in the formula for my static enthalpy rise for rotor divided by static enthalpy rise in the stage, we can write down this equation in sense of UCA alpha 1 and alpha 2. On simplification, my degree of reaction, that's what is coming 1 minus Ca by 2u tan alpha 2 plus tan alpha 1. Now what we learn from our velocity triangle, we can write down by u by Ca1, that's what is equal to tan alpha 1 plus tan beta 1, u2 by Ca2, that's what is equal to tan alpha 2 plus tan beta 2. This is what we have discussed why we are writing u1 and u2. So if I am simplifying this equation, I can write down my degree of reaction, that's what is given by Ca by 2u tan beta 2 plus tan beta 1. So this formula, that's what is defined as say degree of reaction. We can write down this degree of reaction both in relative blade angle, we can write down that in sense of absolute flow angle also. Now if this is what is your case, what we learn, say this is what is my basic velocity triangle at the midsection, you can say. Now for this velocity triangle, we already have discussed how we are plotting our velocity triangle. Let me put this velocity triangle at the tip region. So if I will be putting at the tip region, you can say this is what is my u tip. I will be having my relative velocity component, that's what is v1 dash, and my angle, that's what is beta 1 dash at the entry. Same way if I am considering at the exit of my rotor, I will be having my outlet relative velocity as v2 dash and I will be having my angle as beta 2 dash. So this is what is representing how my flow angle and my relative velocity, that's what is going to change near my tip region. Okay. Now if I will be talking about the hub region, I will be having this kind of configuration at the entry, I will be having this as my velocity triangle at the exit. Okay. Now just remember my degree of reaction, that's what we are writing in sense of Ca by 2u tan beta 1 plus tan beta 2. Now at all stations, if you are looking at hub, at midsection, even at the tip section, my beta 1 and beta 2, they are going to change. If I consider I am having my axial velocity to be constant, this parameter will remain same, and this u, it is nothing but my peripheral speed at particular location. So you can understand, like with change of my radius, my degree of reaction also is changing. So you can say my degree of reaction, that's what is varying from this midsection, it is varying towards the shroud, it is also varying towards your say hub region. Okay. So we are having this kind of diffusion or this kind of degree of reaction variation along the span. Okay. Now let's move towards the next. If I am writing my degree of reaction in this formula, it says 1 minus Ca by 2u tan alpha 2 plus tan alpha 1, and this is what is in sense of beta 1 plus beta 2. Now let me assume my degree of reaction to be say 50%. When I say my degree of reaction, that's what is 50%. So I can write down this degree of reaction as 0.5. And if I try to simplify this equation, I will be coming up with the kind of configuration where it says my 10 alpha 1 and 10 beta 1, they both are same. It means my alpha 1 and beta 2 are same. In other sense, it says my alpha 2 and beta 1, that's what is same. So it says my alpha 1 and beta 2 are same, alpha 2 and beta 1, that's what is same. Or in other sense, if we are putting in sense of velocity term, it says my absolute velocity at the entry of my rotor and my relative velocity at the exit of my rotor. Same way, my entry velocity, relative velocity at the entry of my rotor V1 and my exit absolute velocity, they both will be coming same. So we will try to understand what is the physical meaning of that. If we say we are having this alpha 1 and beta 2, that's what is same, and alpha 2 and beta 1, that's what is same. So in your velocity triangle, you can say you will be having change of all these angles. If this is what is a kind of configuration, we can say that's what is called symmetrical bleeding. We will see what we mean by symmetrical bleeding. It says when I write, say, my degree of reaction, that's what is 50%. So it implicates like 50% of my diffusion, that's what is happening in my rotor, and remaining 50%, that's what is happening in my stator. Okay, and this is what is giving us idea how good the diffusion, that's what is happening within my passage. Now let me tell you, say, when I have started with the discussion for the construction of axial flow compressor, that time we were discussing, say, purpose of my rotor, that's what is to have conversion of my kinetic energy into potential energy, or we can say that's what will be giving rise of my pressure. And purpose of stator, it was to guide the flow. But looking to this, you just realize we are having stator, they are also doing the diffusion work. So now the thing is, it is not only to guide the flow. There are many designs where people, they are doing diffusion both in rotor as well as for stator. Okay, so we need to understand one part here, like how we are dividing our diffusion work. That's what will be giving us what will be my degree of reaction. Okay, now here if I'll be putting my symmetrical kind of configuration, so suppose if I consider my flow, that's what is entering with some absolute velocity at rotor. Okay, so like here if I'll be writing, I will be having my angle, that's what is alpha 1, and based on your velocity understanding, I will be writing my flow which is entering inside my rotor with my relative velocity V1. Okay, and that's what will be coming out from my rotor at some angle, we say that's what I say my angle beta 2. Now according to our concept for 50% reaction, what it says, I am having my alpha 1, that's what is equal to beta 2. So here if you say this is what is my alpha 1, that's what is equal to my beta 2. Okay, same way we can say what is my absolute velocity at the entry, that is C1, it is same as my relative velocity at the exit, which is V2. Okay, and here if you look at careful, if we are doing this kind of configuration, my absolute velocity, that's what is coming out from my rotor, that is going to be large. Okay, so my C2, that's what will be going to be large. Now with this absolute velocity, my flow that will be entering inside my stator, and we are looking for our exit to be suppose say axial. Under that condition, I will be having my diffusion, that's what will be happening from C2 to C1. Okay, so this is what is representing my velocity triangle when I am having my flow which is entering at some angle alpha 1 using my inlet guide vane. Okay, where I will be having my alpha 1 equal to beta 2 and I will be having my beta 1 equal to alpha 2. Okay. Now let me consider, suppose say I am having my flow entry, that's what is happening axially. So you can say this is what is representing my flow entry, that's what is say axial entry. If that's what is your case, according to our understanding for symmetrical blading, my alpha 1 that's what is coming to be 0. Okay, that means my beta 2 is coming to be 0. So you can say I am having my entry to this rotor, it is axial, my exit to this rotor, that is also axial. Okay, and I will be having say this absolute velocity component, that's what is coming to be large, and that's what will be passing through this stator passage, and that's what is giving me what we say in sense of diffusion. So according to what we have learned, say degree of reaction to be 50%, maybe you can make your velocity triangle accordingly. Just look at carefully, saying like what inlet condition, that's what is given, whether you having axial entry or it will be at certain angle. Okay. Now let's move to this particular chart. This is what is a very good representation and very good understanding what we mean by having your degree of reaction. Okay. So very first, that's what is representing my rotor and stator combination, we can say as a stage for which my degree of reaction is say 0. This is what is representing my degree of reaction to be 4.5, and this stage, that's what is representing my degree of reaction to be 1, or say 100% reaction. 0.5 I will say 50% reaction, and 0 I say 0% reaction. Okay. Now what we have understood, my degree of reaction, that's what is basically representing what is my enthalpy rise in my rotor and what will be my enthalpy rise in my stage. Okay. So here if I consider my degree of reaction to be 0, the meaning is my enthalpy rise in rotor, that's what is 0. So if I am plotting my variation of pressure, you can say my entry station is 1, my exit station is say 2 for the rotor. From 1 to 2 I will not be having any rise of pressure. So that's what say my pressure remains constant. Okay. Now if you look at carefully, it says when I am having my degree of reaction to be 0, under that case have look at this passage of the rotor. So here if you look carefully, my entry area and my exit area, they both are same. Okay, it is not having any change of passage shape. So this is what is a kind of blading, it is called impulse kind of blading. Okay, mostly this kind of rotors are supersonic rotors. They have their special application. As and when it will be coming, we will discuss. Okay, now it says I am having my passage area at the entry and my passage area at the exit of rotor, that's what is constant. Now what happens? From this station 2, my flow will be entering inside my stator, and if we go carefully here, this is what is my entry area and this is what is my exit area. So you can say my stator, that's what is having say diffusing passage. So you can say because this is what is making a diffusing passage, I will be having my rise of pressure from station 2 to station 3. Okay, so this is what it says when I am having my degree of reaction to be 0, then there is no pressure rise, that's what is happening in my rotor. The whole diffusion or pressure rising, that's what is happening only in stator. Okay. Now let's move to the next case. It says when I am having my degree of reaction to be 50%. So what we realize, say 50% of my diffusion, that's what is happening in my rotor, and 50% diffusion, that's what is happening in my stator. Okay, if that's what is your case, you can look at carefully. I will be having my rotor passage entry area and exit area, they are different. Okay. Same way, if we are looking at what is my entry area at the stator and what is my exit area at the stator, they both are different. That means my entry area is lower, my exit area is larger. So here if you look carefully, what it says, if I am talking about the pressure rise, it says from station 1 to 2, I will be having the rise of pressure, and remaining pressure rise, that is what is happening from 2 to 3 in my stator. Okay. So this is what is the physical meaning of what we say 50% reaction. Okay. Now here if you look at, this is what is my third case where my degree of reaction, that is what is coming, say 100%. So what is the case? If you look carefully, for my rotor, now I will be having my passage area, that is what is changing from entry to exit. Okay. So you will be having the diffusion, that is what is happening only in rotor. And if we go carefully here, in this case my stators are of impulse type, where I am having my entry area and my exit area to be same. Okay. So this is what is giving us idea how my blade shape, that is what is changing. Let me tell you, when we have started discussing about the degree of reaction, that time I told this degree of reaction, that is what is a parameter which is changing from my hub to tip. Okay. So you can say maybe near hub you will be having some degree of reaction, maybe at midsection you will be having some degree of reaction, at shroud you will be having different degree of reaction. Okay. So this is what is giving us the passage shape, that is what is changing between rotor blades and between my stator blades. Okay. Now here it is written, say most of the German designs during Second World War, when the people they were developing say engines, they were preferring to go with say having configuration with the degree of reaction to be 100%. Okay. So most of the German designs for axial flow compressor, what you find, they are having degree of reaction to be 100%. Means whole their diffusion they are doing only in rotor. Stator, that is what is only guiding the flow. It has nothing to do in sense of rising of the pressure. Now if you look at for Americans, European or say Russian designs, people they are going with the 50% reaction. They feel it's to go on the safer side. So what passage shape what we are looking at this moment, that is what is very important. Okay. When we look at our velocity triangle, you may be realizing near the hub region we will be having our degree of reaction that will be coming low. Okay. Because my peripheral speed, that is what is lower. And when I am talking about my degree of reaction near the tip region or my shroud region, where I will be getting my degree of reaction coming to be large. Okay. So my degree of reaction, that is what is varying from say hub to shroud. There are many designs in which people they are assuming degree of reaction to be constant. So throughout the span from hub to shroud, they are assuming their degree of reaction to be constant. So when we will be discussing about the design approach for axial flow compressor, we will be discussing different design approaches what people they are adopting these days. Okay. And earlier designs also we will be discussing, and then you will realize in past people they were preferred to go with constant reaction kind of design, say 50% reaction design. Most of the compressors, old compressors, they are designed with 50% reaction throughout the span. Okay. So I am sure you got the idea, you got the glimpse of what we say in sense of Leblin's diffusion factor, and we have introduced the terminology, that is what is called degree of reaction, and we realize this degree of reaction, that is what is a concept applicable to turbines, but here in this case we are using this equally for our compressor, because compressor is a working device That's what will be converting your kinetic energy into potential energy, or in sense of diffusion. So working of my compressor I can make by using this degree of reaction calculation. So now you can understand we are moving more towards the design aspects for axial flow compressors. So one parameter what we have discussed in last lecture, that's what was a diffusion factor. Today we have introduced the new parameter, that's what is called degree of reaction. We will be discussing ahead with more parameters as we go along. Thank you very much for your attention. See you in the next class.